So I'll be presenting our paper, Lighting Consistent Object Transfer Across Radiance Fields. That is the state of my voice permitted. So I will first start doing a quick recap on 3D Gaussian splatting, which was introduced by Kerb and colleagues back in 2023. So this is a technique for real-time novel view synthesis for radiance fields, where a scene is represented as a set of 3D Gaussians with different orientations, positions in space, opacities, and colors. And to render the color of a pixel, let's say this one, the idea is you can splat these Gaussians in 2D, sample their color, and then alpha blend them to get the final color for the pixel. And during training, more Gaussians are allocated in regions that need more detail and removed from regions that don't need the detail. And it works quite well. So this is a video from the original publication where they reconstructed this scene from MIPNERF. And after that, they have this very high quality reconstruction, which you can freely navigate in real time. But what happens if we have a reconstruction like this one, and we want to insert a new object? So as you can see in the beginning of the video, so now, if you just copy-paste the object, it will look wrong because the illumination is from the other scene, and it doesn't have the shadows nor the reflections that match the scene you want to. So we'll be working on this, and the main observation is that diffusion models are strong illumination priors, and I'll do a quick recap on diffusion models to illustrate this point, but this is the motivation for our work. The idea is that diffusion models work in two stages. During training, you have a data set of images, and you add noise to the images gradually until completely destroying the signal, and you have a completely noisy image. And on the other hand, you have a learned neural network that learns to gradually remove the noise. So you can, at the end of training, start from a pure noise image like the one on the right, and you can gradually remove the noise until getting a clean image. And this is the diffusion process in action. So again, you can see how we start from complete random noise, and as the iterative process goes, we end up with a clean image in the end. And based on these diffusion models, some works like this one by Poirier-Ginter and colleagues, where they fine-tune the model on a multi-illumination dataset, enables relighting of images and also radiance fields like this one. And another illustrative example is LightLab, which can take an image and can edit it to turn on and off the lights present in it. And you can also change the color of the lights. So based on these works, we propose a diffusion-based harmonization approach for 3DGS scenes. And our method will allow us to take an object from one scene, place it on the other, correct illumination so it matches the target, and make it look realistic. So we begin by inserting an object in a scene, and we design a user interface for this, where we have inserted a track, for example, and the user can freely adjust the scale, because the scale of the scenes might differ. You can also rotate it to make it align with the floor of the target scene, and you can move it freely in the final position that you want. But as you can see here, we still have the same issue. There's no shadows under the track, and the lighting is inconsistent with the rest of the scene. So to deal with this, we propose this harmonization diffusion that will map. What we have on the left is the composite image of inserting the object directly, which has, again, no shadows, the wrong lighting. And the idea is that it will map it to the correct harmonized view on the right that has the shadows and the correct illumination. To do this, we take a pre-trained diffusion model that was originally training to map noise to an image given a text prompt of the image that you want to have. But we drop the text conditioning, and we include these two new images as conditioning signal. It's the object mask that tells us which is the part of the scene that we actually want to harmonize, and the naive composite where the object was copy-pasted. So to train this, we need to generate these composite harmonized pairs. And the idea is that we will just do an alpha blending of of a background image and a foreground that I will describe next in more detail. We have 3 sources of data. So first one is synthetic data from Blender scenes. We have 30 high-quality indoor scenes, and we manually annotate them with multiple cameras and annotating which objects are visible for each camera for this procedure. And these are just 3 examples of the kind of scenes that we have. And this gives us roughly 2,000 input images, but almost 50,000 targets. The targets are more than the inputs because for each image we can choose a different object, basically. And the way we construct the data is, let's say we have the harmonized image. This is just a Blender rendering of the scene from a certain point of view. We can just render the background because we can subtract the object from Blender and just render the background. And next, we can just take the object and render it under a different illumination and paste it back there. So we have the inconsistent composite and the target harmonized view. So, but this data is not enough. So we use actually more generated data using the Flux, the diffusion model, where we generate examples like this, object-centric scenes, to roughly have twice as many images. And the idea here is that we use a template prompt like this one, where the values of the object, the environment, the lighting, and the angle are taken from a set of predefined prompts. So in the end, we have a nice variety of combinations and scenes. And so in this case, unlike the Blender scenes, we cannot just subtract the object and render the background. So we actually use the synthetic scenes to train an object removal network, which will take the harmonized view on the right and give us the background on the left. And, but still, we need to place the object with a different illumination. So we use an off-the-shelf relighting network that relights the whole image. So you have the clock in the middle, which is under a different illumination. And then you can just take it from that image and copy-paste it on top of the background, and you, similar to what we did with Blender, you can produce the inconsistent composite. And finally, we take some real data from the Orida dataset by Kim and colleagues. They have the dataset with background images and with an object on it, so basically the left and the right parts of here. And to get the relate image, again, we use the off-the-shelf network. And in this example, what we can do is we can just segment the DAG from the image in the middle and paste it on top of the background, and we have the inconsistent composite. And this is just an example of more images with the 3 sources of data. So each one of them has its own contribution. As you can see here, the numbers, these are numbers computed against a test set of images of all the data sets and average. But in general, you see, if we remove the synthetic data, the metrics drop quite a bit. Also, if we remove the generated data. And for the real data, it's not that clear. We get a slight decrease in PSNR and FID, but a small increase in SSAM and LPIPs. So that one is not that relevant, and we think that's because the scenes are, in the end, quite simple, and they don't give us much gain. These are some comparisons with other harmonization methods. So we have LVM is latent bridge matching. The main issue with them is that they struggle to actually get the shadows under the objects, making it look unrealistic. MB Collide has an issue with out-of-distribution scenes. They were trained on their synthetic dataset and lower resolution, and they struggle for this. And Nano Banana actually adds the shadows, but if you can see, for example, in the track, the shadow is super strong and it doesn't really match the rest of the scene. Okay, so in this case, now if you go to our column, you can see in all the cases the insertions look realistic, but the harmonizations are independent in the case of the 3D scenes because we want to apply this to each frame of the scene. And the problem is that if we just want to train 3DGS on these images, we have the risk of averaging out the inconsistencies and producing blurry results. So for this, we propose a post-optimization that will, of course, first run the diffusion model on each frame of the target scene after inserting the object. But we carefully designed this 3DGS post-optimization to to end up with a consistent 3GS representation after harmonization. And the main things here is that we can fix the geometry of the object and the target scene because they are already converged. And we only need to optimize the color of the Gaussians. That stabilizes the geometry quite a bit. And we can use a perceptual loss instead of L1 and SSAM because a perceptual loss focuses on higher level details of the image rather than the pixel-wise differences. So there's less risk of averaging out the inconsistencies. So here it's an example of the post-optimization running. I think it was a bit fast, so maybe I can do this. So you can, like, yeah. So you can see that gradually the shadows start appearing, especially on the back part of the track. I think it's a bit easier to see here. Whoops, this area here. I'll just run it once more. Oops, there it is. Okay. Well, I think I can't run it once more. Anyways. And this is just to illustrate the difference between the photometric and the perceptual loss used for this. These are two examples. When the one on the top, you can see this like annoying artifact in the shadow. And the one on the bottom, you can see that the photometric gives this blurry result instead of having a well-defined edge for the table. And some results now. So this is the example from the beginning. You can see that we can correctly match the illumination and add the shadows of the scene. Here's another example where this couch was inserted, and actually here on the right side you can see that the couch has the shadow corresponding to the light coming from the window. An next example of an indoor scene here. This one is an interesting example because the inserted object has an uneven illumination, and our method managed to correct it as well. Here, as well here. This one, you can also see the view-dependent reflections on the table. And also some outdoor scenes. You can see the shadow under the helicopter, under this carriage, and in this vehicle here. And some real scenes as well. So we have the track in the garden from Nipner from the beginning. We have the desk inserted in the London apartment from Sipnerf. We added the locomotive on the left to this scene. In this case, the ping pong table. And the full set of chairs and the table here as well. So for comparisons, we compare our method mainly with inverse rendering methods that estimate in some form albedo and lighting of the scene. And in that case, you can run these inverse rendering methods to the source scene and the target scene, insert the object and re-render. But as you can see, they struggle quite a bit with especially some type of objects like the hot tub, they really struggle to actually get it. And they cannot add new shadows to the object. So in the end, the insertion always end up looking unrealistic. And also some metrics, because we have those synthetic scenes with ground truth insertions. And you can see that in all cases, we outperform them by a large margin. So hopefully by now you understand how we managed to get this insertion in the original 3DGS scene. A quick summary is that we use the diffusion models as illumination priors. We create a data set of synthetic, generated, and real data. We develop this model for single view harmonization, and then we propose this multi-view consolidation to end up with a consistent 3DGS representation. If you want access to our code, our data, and models, you can scan this QR code. And finally, I would like to thank the ERC NERFIS for funding this research. Thank you.
Great work. Thank you. Are there any questions? Yes.
Thank you for the presentation. In your demo, when you put the track, I see there are some reflections that also projected on the ground at distance, and those are not covered by the mask. So will that be leaked? Where this reflection come from?
So basically, you mean that the mask doesn't cover the shadows?
Doesn't cover the reflections. There's some leaked color reflections that is projected on the ground, on the grass, basically, and it was not covered. I don't know, like, is that because the data was not clean, or?
Let me check
I think
that.
it's at the very beginning, I think maybe page 4 or?
Here.
Yes, this one. So can you replay the video a bit?
Yes. How can I? Okay, there it is. You mean when it's like being moved?
Yeah, you see?
You mean these things here? Like here when it moves?
Yeah, you see there's some reflection that project on the rocks.
Yeah, I know what you mean. Those are not reflections, those are floater Gaussians from the segmentation.
Okay.
Because the segmentation is not perfect and you see them moving around, actually, because they are just floating there, and yeah, it's not a reflection of the track on the grass, it's an artifact of the segmentation in 3D.
So will that be corrected or not?
Yeah, I mean, I think it's barely noticeable, but yeah, I observed that it's corrected because the model is not restricted to what's only in the mask. Because, I mean, obviously, it's not restricted what is in the mask because it can add the shadow, but you don't have a mask for the shadow as well. So it can correct stuff outside the mask in general. But this is not a reflection, it's an artifact from the 3D segmentation.
Okay, thanks.
Thanks for the presentation. I think the results are interesting. My kind of like a concern with this methodology in general is,
yes.
Okay, so you say that you use the diffusion models as a prior for the
yes.
relighting, but this is kind of like this is a plausible result.
Yes.
But what do you think about the validation part? Like, because for example, if this diffusion that is your prior hallucinate the physics, maybe it looks good, but it's not realistic physics. Yeah, it's not realistic.
I agree. Yeah, that's true. So yeah, our model can only produce plausible-looking results. It's not guaranteed to be physically correct, of course. Yes, in general, that if you want to do something more physically based, let's say you want to estimate albedo lighting and try to do something like that, then you will also run into some issues because I mean the model is not perfect. And it can also introduce error. Maybe it's more physically grounded, but still it won't be perfect. And to account for that in our evaluation, we not only introduce the reconstruction metrics, we also have FID that will measure similarity at a distribution level. So we think that's a proxy for realistic looking. But yeah, I agree. Our model can produce plausible results. They are not guaranteed to be physically accurate.
But I mean, I think something that you could explore for the validation is try to maybe with a collaboration is a light stage, with a light stage.
Yes.
You can do the relighting. I mean, you capture an object with different lights, and then you can relight it in any environment. So this could be kind of like your ground truth without the inverse rendering. The problem is the capture device, but I mean, it may be something interesting to explore there.
Okay, yeah, sounds good.
Thanks.
Yeah, thank you.
I think there was one more question over here.
Oh, hello. Thank you for the great talk.
Yeah.
I just wanted your opinion on why, how far can synthetic data alone go, and why do you think you don't get the best results from synthetic data alone? Like Blender.
I didn't get the last part. Why don't you? You said something like, why don't you? But I didn't get what you said.
Why don't you get the best results from using synthetic data alone, let's say rendered in Blender?
I think synthetic data can take you very far away. In this case, I think one of the problems is the scale of the data. If you see, we are just fine-tuning with a couple thousand images, so that probably has to do with that. But in this case, the synthetic data is probably the strongest source because of the accuracy you can get. The generated data helps, but the correct data is the synthetic data because that one was rendered with the path tracing, so you are sure that like the physics of the rendering are right. So I think you can go a long way with it, provided that you scale it up. The problem here was the annotation. Annotating the 30 scenes took me a couple of weeks, so if you want to scale it up more than that, it will take even more time.
I think we have time for one more question, maybe here.
Can you go back to the train scene, please? And thank you for the presentation.
This one?
Yeah. Yes, so for that one, like what I noticed is that the real train shadow is basically blue because like most of the sky is blue, but the false train shadow is black. So I was wondering, like, do you think there's a way? Is it something that's lacking from the dataset, or do you think there's a way to maybe include some additional single scattering or something like that?
An additional what? Sorry, I didn't get it.
Sorry, so the real train shadow is bluish because the sky is blue and like there's like all the not just the sun direction that does the shadow, but the new train, the shadow is purely like black and gray. Yes. So like, is it something that's missing from the dataset that you use, or do you think there's a way to maybe enforce some additional single scattering to try to get that back? Or?
So on the one hand, even if our method works here, I would like to stress that there's still like a big domain gap because this was trained exclusively on indoor scenes. Okay. And this is an outdoor scenario with an object that it's never seen because you are very unlikely to have a locomotive in your kitchen. But so the model has that bias, for sure. One thing, I guess, if you want to have some more control on the, let's say, the color of the shadow, is, maybe you remember I said that we drop the text conditioning. I was thinking that it could be a way of actually having like a prompt description of the type of result you want in the end. We'll give you an extra control if you want at inference time where you can specify maybe the color of the shadow and stuff like that.
Okay, thank you.
Awesome, thank you.
Thank you.
Let's thank our speaker again.